Hello students. Today we're going to look at modeling with quadratic functions. And what that means is we're going to look at real-world situations where some sort of behavior is modeled off of a quadratic function, and we're going to use what we know about quadratic functions to learn more about that real-life scenario. So we have recently been looking at transformations of functions, and we saw that we could use transformations of functions to transform f of x equals x squared into any quadratic function in standard form, f of x equals a times x minus h squared plus k. And when we do this, the vertex of the parabola has coordinates h comma k. Now, to go from a normal quadratic function, f of x equals ax squared plus bx plus c, into this standard form, we had to complete the square. And we're going to see some situations where that ends up being very challenging. We might have fractional or decimal coefficients, and we don't really want to do that. So what I want to do is to develop another way for us to figure out where the vertex is going to be, specifically if we're dealing with a function in the form f of x equals ax squared plus bx plus c, and we might have coefficients that make completing the square challenging. So what we're going to do now is going to be a bit intense algebraically. We're going to develop a formula to find the vertex instead of in terms of h and k, in terms of a, b, and c. And you're not going to be asked to reproduce these calculations later. What we're going to do is we're going to go through some complex algebra, and then once we know how to find the vertex, we won't have to go back to this again. We can just use the formula for the vertex. So what I'm going to do is I'm going to go through the process of completing the square, but instead of using numerical coefficients, we're going to be dealing with variable coefficients. So remember, when we completed the square, the first thing we did was we factored out the leading coefficient from the first two terms. If we do that, that's going to give us a times x squared plus b over a times x. And then again, we're going to leave that constant term off at the end. Now, once we do that, we need to go through the process of completing the square, which means we need to take the coefficient on the x, divide it by 2, and square it. Dividing by 2 is the same as multiplying by 1/2. If we multiply this by 1/2, we get b over 2a. And if we square that, that gives us b squared over 4a squared. But what we're really adding is a times b squared over 4a squared, and one of the a's cancels, leaving us with b squared over 4a. So we also have to subtract b squared over 4a to balance things out. Now we can factor what's inside the parentheses. This is going to give us x plus b over 2a, quantity squared. And then on the outside, we have c minus b squared over 4a. We can leave this like this, or we can combine those as fractions. I'm going to write it both ways. All right. If we combine these as fractions, the least common denominator is 4a. And if we write this as a fraction, it's going to be 4ac over 4a. So we're going to have 4ac minus b squared over 4a. And this is how we can write a generic quadratic function, ax squared plus bx plus c, in standard form. And when we do it this way, we see that the vertex h comma k is actually given by, remember h comes from whatever's being subtracted from x. In this case, that's going to be the opposite of b over 2a. And then k is the constant term. In this case, it's 4ac minus b squared over 4a. So we could memorize all of this, and this will give us the vertex without having to complete the square. Now, I don't know about you, I don't want to have to memorize all this. I would rather memorize fewer things. So an easier way to do this is to just memorize the formula for the x-coordinate, the opposite of b over 2a, which we've seen before, and then just say that we plug it in, and that will give us our y-coordinate. So here our vertex is going to be the opposite of b over 2a, that's the x-coordinate, and to find the y-coordinate, we just evaluate the function at whatever that value is. So this is a shortcut for us to find the vertex of a quadratic function. And remember that this is going to help us find the maximum or minimum value for our quadratic function. So what we're going to do is we're going to jump straight into the video examples. I've got 3 examples that I've prepared. Each of these is a real-life scenario where we have some quantity that's relationship is modeled off of a quadratic function, and we're going to use this and what we know about quadratic functions to figure out some maximum and minimum values. So it's really important to me that you watch all of these examples so you can see some real-life situations where knowledge about quadratic functions helps us learn some important information.